example of a binomial. We sometimes need to expand binomials as follows, but doing this direct multiplication can be rather difficult for larger powers or more complicated expressions. Pascal's triangle, it is named after the French mathematician Blaise Pascal. In mathematics, it is a triangular array of binomial coefficients in a triangle. As n becomes larger in the quantity a plus b raised to n, the more laborious it would be to use the Pascal's triangle. This is more prone to error or can increase the possibilities to commit mistakes.
So the binomial theorem is a theorem used in mathematics in expanding binomials to a certain degree. It does not require laborious work unlike the Pascal's triangle that was discussed a while ago. But before we can truly understand the concept of binomial theorem, let's first have a review of the concept of combination. So combination is expressed in three forms: NCR, C quantity n, r, and the quantity of n and r with both overlying at the top and the bottom. So it is written as n taken r at a time with the formula of n factorial all over the quantity of n minus r factorial multiplied to r factorial. So instead of the Pascal's triangle, the formula of combination is used to find the coefficient of the terms. Let's also take note that when it says the quantity of a plus b raised to n, it says that there must be n factors of a plus b, and n is any positive integer. With that being said, we can say that the quantity a plus b raised to n is equals to the combination of n taking 0 at a time times a raised to n b raised to 0 until n taken n at a time a raised to 0 b raised to n, where the r plus 1 term is equals to the combination of n taken r at a time is equals to the formula of combination n factorial over n minus r factorial times r factorial, where r is not equal to 0 and not less than 0, but not greater than n and equal to n. So in summation, a plus b raised to n is equals to the summation of n taken r at a time with the combination of n taken r at a time, a raised to n minus r is equals to b raised to r. This is the formula for binomial theorem. Now that we've discussed the introductory part of the binomial theorem, we will answer the question, how really does the binomial theorem help us find a shortcut in finding the terms of a binomial expanded to a certain degree? So now we're going to discuss the patterns formed in binomial theorem. We are actually given three: the number of terms, the variables exponents, and the binomial's expansion's coefficients. So let's start with the number of terms. So we are given binomials raised to a certain degree, and we can see the pattern that when x plus y is raised to 0, it has one term. When raised to 1, it has 2 terms. When raised to 2, it has 3 terms. When raised to 3, it has 4 terms. And 4 terms, it has 5. So, the pattern we see for the number of terms is, when the binomial x plus y is raised to a degree n, it has n plus 1 terms. So, let's now go to the exponents. Given the same value for x plus y, we can see there are also patterns with the exponents, for the x exponents and the y exponents. Let's start first with the x exponents. The x exponents decrease from n to 0. So for example, x plus y raised to 5, there are no value for x in the last term, but x has the full value of 5, which is n. For y exponents, it increases from 0 to n. So for the first term, it has no y variable because its exponent is 0, but in the last term, the y has a variable of 5, which is also equal to n. So for x exponents decrease from n to 0, and y exponents increases from 0 to n. We also observe that the sum of the exponents, no matter the value of the exponent, is always equals to n. So for the first term, it has 5, which is the number of n. Then for the second term, we have 4 plus 1 also equals to 5. Third term, 3 plus 2 also equal to 5. Then so on and so forth, all of them are equal to 5. And now finally for the binomial coefficients. So for the given x plus y raised to 5, here are the coefficients and the answers for the expansion. So we actually have three observations. So for the first observation, the first and last coefficient.
So let's now move on to our example. So for the first example, find the fifth term of the expansion, quantity x squared plus 3 raised to 6. So you are given in our formula. We will just substitute n and r and we will find the answer, 540x raised to 6. For our second example, we are given to find the first three terms of the quantity 2x minus 5y raised to 7. So we are going to have three solutions here. One for r is equals to 1. The second is for r is equals to 2. And the third is r is equals to 3. We will use again the same formula, but we have to understand that the given is a difference of two terms and not a sum, just like what we've discussed earlier. So basically, we will just use the same formula, but we'll be cautious about the sign. So going with the solution, our first answer is 128x raised to 7. Our second is negative 2240x raised to 6 times y. And the third is 16,800x raised to 5y raised to 2. Let's now move on to our last example. Find the middle term of the expansion. Call it 3x plus 2 raised to 10. So we're not actually given a specific value of r, so we have to find the value of r. So our given is find the middle term, so we have to first find the number of terms. So the formula for number of terms is n plus 1, and since our n is 10, our number of terms is 11. Its middle term is 6, and if we are actually, because it is the value for the number of terms is actually odd. If we are given an even number of terms, there are actually two middle terms. But in this case, we're only going to use 1. So the formula, we're going to use the same formula, and applying the given to the solution, our answer is 1,959,552x raised to 10.